Send her a picture of your notes too. Okay, so it's kind of hard, and I don't know if y'all have seen the video already. It's kind of hard to actually see clear pictures of it, like to see this so clearly on the camera. So I'm hoping that while I'm talking and writing, you're like listening to it and then you're filling it in if you have to watch the video part. But it would be awesome if somebody in class and, hey, I didn't make it, can you snap me a picture of the notes? Because it would be a little clearer to have it in front of you. So if y'all can, that would be awesome with each other. So let's go ahead and talk about the notes right here. Make sure you have your name on it, right? Because everything down, and that's again the reason why it took me so long, I really debated, is gonna be given to me in person, no more Blackboard, and we're gonna see each other 2 days a week and no Friday classes that we have to meet on, okay? So let's go ahead and start with bonding. So it says here, why do atoms bond? Well, they actually bond so they become more stable. This is how they're gonna, remember, they become like that quote unquote ion. This is how they gain or obtain those extra electrons that they need, or how they get rid of. And they do it, a lot of them, they just do it through bonding within somebody else. So it says here, what makes an atom stable? Well, a full valence shell. That's what makes it stable once it has those 8 shells on the, those 8 valence electrons on that outer shell. It says here though that most, and again we're using that word most, atoms need 8. Now don't forget though, we call that the octet rule, right? 8 valence electrons, except for, well, here's a few exceptions, and I know I've already told you we're gonna have a lot of exceptions throughout the school year. Helium and hydrogen, because they just need to have 2 on that outer shell. They only have 1 shell out there, they can't have 8. So they only need 2. It says here, let's talk about the word ionic bonding, because there's a difference between what we call ionic bonding and covalent bonding. Ionic bonding occurs between a metal and non-metal. And I skipped that up there, didn't I? Let me go back to the previous sentence. Atoms are going to do whatever they can, so that way if they have to, they will share, comma, they will or gain or lose valence electrons in order to obtain those 8 or that octet rule. And a lot of this occurs through the bonding, okay? But not anyone can bond with anybody else, right? There's limits here. So, ionic bonding, letter A, metals and non-metals. All metals are going to be cations, remember, and they are positive. All non-metals are going to be anions, which are negative. Part B, it says here that metals become positive ions. Why? Because they lose electrons. Non-metals become a negative ion because they gain those electrons. The number of electrons donated must equal the number of electrons accepted. And what do they mean by that? Well, they mean that group 1 can bond with group 17 easily. Hey, I have 1 extra electron. Hey, I need 1 electron. It works out perfectly fine. Group 1 is not going to bond, like one group 1 atom is not going to bond with a 1 single group 16. It just doesn't work like that because they're not going to end up with that full valence shell. Okay? Now it says here though, examples. We've got, let's combine calcium and fluorine. So valence electrons for calcium. What group is calcium in? Calcium is in group 2. So I'm just going to put a little note here. If we don't remember, valence electrons are going to be the group number. All right. And so it's in group 2, so it has 2 valence electrons. Valence electrons for fluorine. Fluorine's over in group 17. So they have 7 valence electrons. So when we look at this, it says here electron dot structure. Well, the electron dot structure, or the Lewis dot structure, is super important to us. Remember, there's the Bohr model and the Lewis dot. Why do we not like the Bohr model? Because it has all of the electrons. And if we're talking about element number 52 or 78, that's a lot of little dots to add around there. And those inner electrons, they have no meaning because they're there. They don't have any jobs as in when it comes to the bonding. So the Lewis dot is the more important one because that's where the bonding is going to occur. So let's look at this. If we had to draw this out, I'm going to go ahead and put Ca. And Ca has 2 valence electrons, one at the top, one on the side, so 2. But what about fluorine? Okay? Now, is one element or one atom in group 2 going to be able to combine with one atom in group 17? No, not just one, because they're still not going to end up being full. What do you mean? Fluorine, who is F, and it's in group 17. 1, 2, 3, 4, 5, 6, 7, has an open spot over here. And so this electron is going to come over here and bond inside there. But again, like I said though, we can't just have 1 and 1. If we needed to, we can have more, and that's okay. So in this instance, this calcium still has an extra 1 valence electron just sitting out there. So what makes it convenient is if we find another fluorine, 1, 2, 3, 4, 5, 6, 7 valence electrons, and that extra one's going to come over here. So could we have somebody in group 2 and group 7 bond together? We could, but it's going to be more than just 2 atoms. It's probably going to have to be 3 or 4 or something else. Okay? So it says here, let's look at this. The oxidation number we're looking for calcium is a +1 charge. The oxidation number over here, though, is a -3 charge. The number of sodium, oh my God, keep jumping. I hope y'all are like saying, wait a minute, Miss Munson. I'm jumping to the next sodium one, and I'm looking over here, so forgive me. Now let's go back over here. Looking at the oxidation number, okay, if this side is calcium, so this oxidation number is for calcium still, it's going to be, look at this, a +2. Why a +2? Because those 2 valence electrons left the calcium, bonded with the fluorine here, okay? Made him happy, right? Because now he got rid of those extra 2. Looking at the fluorine over here, fluorine's in group 7 or 17. He, right here, gained 1, and I'm just looking at the individual fluorine, who has a -1 electron or -1 oxidation number. Calcium, it says here, the number of calciums needed, I only needed 1 calcium to bond here. How many number of fluorines did I need? I needed 2 fluorines to bond over here. Okay, and we're going to take this up, more, it's going to make more sense, a little better, give it a little time. Example number 2, here's where I was trying to jump ahead, the sodium and the nitrogen. So let's look at how many valence electrons does Na have? Again, it's the group number. Na is a metal in group 1, so in that case, they have 1 valence electrons. So nitrogen is a non-metal in group 5 or 15, so they have 5 valence electrons. So it says over here, let's go ahead and do some Lewis dot or structures, right? Just the valence electrons, and let's see what we can do. I'm going to go ahead and I'm going to put the nitrogen. There's a reason why we put the nitrogen first. Once we do this, you're like, oh, that's probably why the nitrogen is first. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. There's a spot here, and a spot that's here that's available, right? And it's easier to take in 3 valence electrons or 3 electrons than it is to get rid of 5 electrons. So who is he going to bond with? Well, we're telling him that he's going to bond with sodium, Na. Now, sodium, Na, only has one valence electron. So this Na right here, or this one, is gonna get rid of and come over here. But nitrogen is still unhappy, so he's gonna need, he's gonna need another Na, and that valence electron is gonna bond inside there. Still not happy, he's gonna need another Na. That valence electron is gonna bond over here. So when looking at the sodium itself, and just looking at one sodium, because I understand there's 1, 2, 3, what is the oxidation number just for that one sodium? Well, it's a +1 charge, because I can see that this valence electron left the sodium and went over to the nitrogen. The number of NAs needed for this bonding to occur, well, 3. The oxidation number for the nitrogen, it has a 1, 2, 3, a -3 charge, because it needed 1, 2, 3 electrons, so that way it could be full. So how many? I only needed 1 nitrogen to bond with 3 sodiums. Okay? And those numbers are going to be important in just a moment when we do crisscrossing, so hopefully it'll make sense a little bit more in just a moment. So it says here, let's talk about crisscrossing with ionic bonding. One more time, what's ionic bonding? Ionic bonding is when we get a metal and a non-metal versus a non-metal and non-metal, which is covalent bonding. How do you memorize that, Ms. Munson? I think it's ironic when two things that are opposite come together, a metal and a non-metal. Okay? So because when two things are opposite and they come together, it's really ironic. Okay? And so that's how I remember ionic bonding. So let's keep going. Next part here, crisscross ionic bonding formula shortcut. Because rather than us drawing the Lewis dot structure, which is what we could do, we can do a shortcut method, which makes a lot more sense than drawing this all out. So this is the long method, and this is gonna be the shortcut method of being able to come down to this information down here. So it says, number 1, find the charge for each element involved in the bond. Okay? Number 2, crisscross the number from each of the partner's charge so that it becomes the number of atoms needed to bond to fill up the valence shells. Number 3, double check that the formula is in the lowest ratio and cannot be reduced. That is super important. If anything, I have a lot of students in the beginning that forget this part right here. They forget to reduce it, okay? If you can reduce ionic bonds, you must reduce them, okay? But again, for ionic bonds, there are rules to being able to bond things. And then the next one here says, the overall charge on the compound should equal 0. And I'll show you what I mean by that. It must equal 0. So mathematically, it says here, you can justify that it equals 0. Okay, so after a while, you don't even need to do this mathematical justification. But in the beginning, it might help you, so that way you're like, oh, that makes sense. I did it correctly. So let's go ahead and let's practice over here, examples. So calcium. Calcium is a metal in group 2. So let me put a 2 over here. Fluorine is a non-metal in group 17. What is the charge? It's going to be a -1, and that's a +2. So find the charge for each element involved in the bonding. I did calcium +2, fluorine -1. Step 2, crisscross the numbers from each of their partner's charge, so that way it becomes the number of atoms needed for the bond. How many atoms of sodium did I need? NAs? I needed 3. How many nitrogens did I need? I needed 1. Well, how many do I need for calcium and fluorine? Well, I'm going to do like it told me, and I'm going to crisscross this down and crisscross that down. And they're going to swap. So now it's going to become Ca. Do I put a 1? Remember, we don't put 1s. Okay? So when there is no number, it's indicated as just 1. So we're going to leave that alone. F2. The charge, the plus and negative charges don't come down. We don't deal with those. It's just the numbers that come down and they crisscross. So if I needed to bond calcium and fluorine, I'm gonna need 1 calcium and 2 fluorines to make this bond occur. And if you don't believe me, you can do this drawing over here to the side to double check it. Now, another way to double check it is what we call the math justification, okay? So in this case, I have a +2 charge for calcium. How many calciums do I have? 1. Let's look at the next one. Fluorine, it has a -1 charge. How many fluorines do I have? I have 2. Let's go ahead and we're gonna do this math here. Watch for the little equal sign. +2 times 1 equals a +2. Plus -1 times 2 equals a -2. +2 plus -2 equals a 0 charge. And so that's the math justification. You can do that just to double check yourself, or you can go and do the whole drawing. So one more time, ionic bonding, okay, and that's what we're talking about today, just that one section alone. Ionic bonding has to deal with a metal and a non-metal. How do I remember it? Because it's ironic when 2 different things bond together. Now, there's a couple of ways to do this. When you're gonna bond metals and non-metals to see how much you need, right? You can either do a drawing with using the Lewis dot structure, or you can come over here and you can do the crisscross. After you do the crisscross, you come over here and do your math justification. They should equal out to 0. And you see how they equal out to 0. Here, I do keep my charges so that way they can cancel each other out. Let's do the next one real quick. Over here, it says Na and S. So Na is a metal, and that's in group 1, so that's a +1. All metals have a plus charge. All nonmetals have a negative charge. That was the reason for the beginning up on section 2 where it says ionic bonding. S is a -2 charge, -2 charge. I'm gonna come over here and I'm going to crisscross. So now I'm gonna say Na2S, and I do not add the 1 down here because it's already understood to be there, okay? So I can come over here, let me do my justification to make sure that it works, my math justification. I've got Na, it has a +1 charge. How many do I have? I'm gonna multiply it by 2. Plus, I have sodium over here, it has a where am I at? A -2 charge. -2 charge. How many sodiums? Well, that number behind it, which is invisible, a number 1 is there. We can do our math. 1 times 2 equals 2, plus -2 times 1 equals a -2, plus +2 plus a -2 equals a 0. Super easy now. This is like, oh, this is easy. Alrighty, well, let's keep going. Count aluminum. Aluminum has a +3 charge. Remember, it's a metal, so it's gonna have a positive charge. It's a cation. And then bromine, Br. Br is a non-metal in group 17. So for bromine, it's gonna have a -1 charge. Crisscross those suckers. So Al, do not put the 1, and Br3. So to make that bond, I'm gonna need 1 aluminum atom and 3 bromine atoms, so that way it can bond and everything's gonna be full and happy. So not bad, hopefully. I think this is probably pretty easy cheesy now for you. I'm gonna leave those 2 for you to do on your own, and we're gonna turn the page. Now what about the transition metals? Because they're metals too. And couldn't they bond with non-metals and still have that ionic bonding that's occurring? They could, but remember what we said, what makes them special is that they have more than 1 oxidation number. And I told you, oh, we're gonna get to that point to know and find out what their oxidation number is. Alrighty, so let's go ahead and let's talk about transition metals and how they actually bond with non-metals. So it says here, transition metals, and don't forget Pb and Sn. So why do we say PB and SN? If you look back there on the periodic table, they're both in group 14. They're not in that little square. Or if you have your, what do you call it? We know that all of these are transition metals right here. But it said, don't forget PB and SN. Those also are part of the transition metals. Okay, that's what that's saying. Well, let's keep going. Have more than one charge. Alrighty, not a problem. The oxidation number will be represented by a Roman numeral. Right, and just as a quick reminder, I'm sure you're all good with Roman numerals. 1, 2, 3, and this one's 4, right? So 1 take away 5 equals 4. Just so that way we're all 1, 2, 3, 4. Okay, that's our Roman numerals. And the Roman numeral indicates the charge. All right, so it says here on number 2, write the formula for a compound containing silver 1 and sulfur. Okay, well, let's start off first with the oxidation numbers. What is the oxidation number for silver? It's a +1 charge. How do you know it's a +1, Miss Munson? Because all metals are cations. We said that in the beginning of our notes here, and they have a positive charge. Sulfur is a non-metal. Sulfur is over in group 16, has a -2 charge. Okay, so now I'm going to go ahead and write them down. Silver is Ag, sulfur is S. Let me crisscross those. Ag2 and S stays like as is, right? Because we don't pull down the number 1. Ag2S. So we're going to need 2 silvers to bond with 1 sulfur. That's what those numbers are. They're telling me the number of atoms that are going to be bonding. It's a ratio. Next one, iron. Iron has a 2 charge, so it's a +2 because all metals are cations. Oxygen is over here in group 16, so oxygen has a -2 charge. Let's make sure that we crisscross these suckers down. And now we're going to have Fe, because that's the symbol for iron, and O, Fe2O2. What did we say on the previous page? Because we're still talking about ionic bonding. When it comes to ionic bonding, we need to make sure, because this is the one step that many of us forget. You don't forget it though. Double check that the formula is in its lowest ratio and cannot be reduced. Those can absolutely be reduced, right? So in this case, let's reduce it just like you would in math class. So if you were to reduce it in math class, that would become FeO. That would be the right answer. I'm going to put right here, reduce. And that's how we got our answer, FeO. All right? Again, it just comes down to the rules. Once you kind of have the rules set in your mind and you know them, then it's going to be a lot easier to do the bonding. And then we're going to come up with rules for naming. And then we're actually going to name that, FeO. Okay? We're going to be able to name AgS, Ag2S. Okay? And then the next one, we got cobalt, which is a 3 charge. Again, it's a +3 because all metals are cations and they have positive charge. And chlorine is a non-metal, group 17, a -1 charge. I'm going to go ahead with my arrows just to help visualize it. They're going to crisscross down. Cobalt is CO, and it's going to be a 1, so we leave it alone. And then chlorine is Cl, and we're going to put a 3. And I'm just going to box that in. There goes my answer. Let's keep going because we got this other thing that we have. And again, they're going to talk about transition metal bonding on the video notes. They're gonna talk about polyatomic. That's gonna be its own little section on the video notes. So let's talk about what we call polyatomic. And you may not have heard that word before. Like, what do you mean polyatomic? What does the word poly mean? More, multiple, more than. So we're gonna have more than one non-metal that are together that's gonna bond with one metal, okay? So polyatomic, the word poly means absolutely multiple, more than. So we're gonna have more than one non-metal that's grouped together, and they always come together. They're just like, I don't know, like BFFs or something, you know? They come together. It's like, you want one, the other one comes along with it. And we've got a full chart here of all the well, not all of them, but the majority of the most common polyatomics out there. It's to the point where there's just too much. You just don't memorize this stuff. It's on your formula chart. So when you take your quiz and your test, the polyatomic chart is on there. It's not expected for you to memorize it, okay? Now, it's grouped into, let's look at this, more than one nonmetal, C, H, and O. And everybody in this section has a -1 charge. Everyone in this section has a -2 charge. Everyone in that section has a -3 charge. But, look at this last couple of polyatomics. NH4 and H3O. They have a +1 charge. So the first thing we need to know is that pretty much all polyatomics are pretty much going to be a negative charge. Didn't we say nonmetals are anions that have a negative charge? But there's, again, like I said, a few exceptions to the rule. Even though they're polyatomics, they're going to have a plus charge, a plus over here. But the rest are negatives. Let's go ahead and fill in our notes over here. CuPO4. What do you do when there's more than one nonmetal bonded to a metal? And I can see that over here. This is the metal, and those are the nonmetals bonded to it. Okay? Two or more nonmetals bonded to the metal are called polyatomic ions. How to write a polyatomic compound or ionic compound that contains a polyatomic in it. So we're going to go back, and they're quote unquote different rules, not much different from what we talked about already. The charge given to a polyatomic ion applies to the entire group. What do you mean by the entire group? I mean the whole group over here. If I look at this first row, C2H3O2 all has a -1 charge grouped together. NO2, both the N and the O come together bonded, they have a negative charge that's grouped together, okay? So that's what they mean by the entire group. They mean, when we're just talking about that, or we're talking about that group. The next one, the polyatomic ion exists as a unit, never changes or never change the number of the atoms within the ion. What they're trying to say is C2H3O2 will always be C2H3O2. You don't go and change it to CH3O to try to reduce the C and the O. Does that make sense? You don't do that. You don't mess with them. We're going to have 2 carbons, we're going to have 3 hydrogens, and we're going to have 2 oxygens in this group together. So 2, 4, 6, 7 come together as a group, okay? Don't mess with them, and you don't try to change, you don't try to reduce, you leave it alone, okay? One N and 3 oxygens, you leave them alone. Do not change that little number at the bottom. The next part, if more than one polyatomic is needed, then we're going to place parentheses around the ion and write the number appropriate, or at the bottom for the subscript outside the parentheses. What do you mean more than one group? Well, I mean, for an example, this H and this O come together as a group. But what if I need one group of OH and another group of OHs? we're gonna put a parentheses and we're gonna say OH, and outside the parentheses, we're gonna put a 2. That means there's 2 OHs that are there together. So let's go ahead and let's look at this. We talked about that. Here are the rules. They're really easy, I promise you. It says here, you do not need to memorize them at all, right? Those ions, the polyatomic ions, are on your formula chart. Let's practice. We've got sodium and we've got nitrate. So sodium, Na. Na for sodium is a metal in group 1, so it's going to have a +1 charge. I'm going to put Na, because that's the symbol. Nitrate. The ATE indicates that that is a polyatomic, okay? ITE indicates it's a polyatomic. So nitrate, I'm going to come over here, find nitrate. Nitrate is NO3. That's nitrate. Now, what is the charge for NO3? It's at the top, -1 charge, so I'm going to do a -1. I'm going to crisscross those charges just like I did in the previous one. And so now my answer is going to be NaNO3. Did I need more than one NO3? No, I just needed 1, so no parentheses. If this charge was a 2 and I brought it down, I would have to put parentheses and put a 2 in behind it, okay? So let's keep going to the next one. Aluminum. Aluminum is a metal, it's in group 13, so he's gonna have a +3 charge. Then I have sulfate. Sulfate, come over here, find your sulfate. Here it is, SO, so Al, and then this one's SO4, and that has a -2 charge. Crisscross it, crisscross this, crisscross this. I can see that a 3 is going to come over here. We're not going to have 43 next to each other. We're going to have a parentheses to separate it. So Al2 parentheses SO4 parentheses 3. And that's my answer. Easy. So what are we bonding right now? Ionic bonds. What is an ionic bond? A metal and a non-metal. And there are some where we have more than one non-metals that are together, come in a group. They're called polyatomics. All right? And then we've got, let's see, calcium. Calcium is in group 2, so it's a +2 charge. PO4. PO3 and PO4 have a -3 charge. So -3. Let's go ahead and crisscross those. Cross here. So we're going to have Ca3 parentheses PO4 parentheses close it parentheses 2.